Right, so further maths core mock summer 20 solutions. Question 1. So show the sum of that is equal to that. So we're going to start by multiplying out our brackets. That will give us the sum from r equals 1 to n of r cubed minus the sum from r equals 1 to n, and I'll put the 3 there, of r. So formula we need to know, sum of r, and the formula given in the formula booklet, which is the sum of r cubed. So we're going to put those in. So that will give us 1/4 n squared, n plus 1 squared, minus 3 over 2, lots of n brackets n plus 1. Now I'm just going to rewrite that, which might make it a little bit easier. That's 1/4 n squared, n plus 1 squared, and I'm going to cancel up the fraction, so that's minus 6 over 4 n brackets n plus 1. So I can now take out 1/4, I can take out an n, and I can take out an n plus 1. And inside the brackets, that will leave me with an n plus 1, and a take away 6. So we're going to multiply out the brackets. And that will give us n squared plus n minus 6. And then we're going to factorise what we have in the brackets. So that'll be n plus 3, n minus 2. And so there we have our answer to question 1. Right, question 2. So part A says show that the determinant of A is greater than 0 for all real values of k. So in order to find the determinant of A, that will be equal to the product of those two, take away the product of those two. So that will be equal to k plus 2, take away 3 times minus 1. So that will give you k squared plus 2k plus 3. So there's more than one way in which to show that this is always greater than or equal to 0. So one of the ways is by completing the square. And if we complete the square on that expression, we get k plus 1 squared. So square that and take away 1 plus 3, which will be k plus 1 squared plus 2. Now k plus 1 squared is just a graph of k squared, which is like that, translated 1 square that way. So k plus 1 squared is greater than or equal to 0. So the plus 2 would shift it up 2 places. So therefore, k plus 1 squared plus 2 must be greater than 0. You could also have done it by looking at the determinant, b squared minus 4ac, and that will give you 2 squared minus 4 lots of 1 times 3. So that will be 4, take away 12, and this is less than 0. And b squared minus 4ac less than 0 is no solutions, as the graph does not cut the x-axis and so must be above the x-axis. Right, part B says find a to the minus 1, so the inverse of a. So things we need to know, that the inverse of a is given by 1 over det A multiplied by the matrix, where those two have been switched and the sign of those two has been changed. So that will give us 1 over k squared plus 2k plus 3, which is the determinant. And so we'll switch our two entries, those two, and then change the signs of those. Question 3. So it says that 2z plus z star is equal to that, and what we need to do is find z. So in the form of a plus bi, where a and b are real constants. So one of the first things to do is to rationalise the denominator of the right hand side. So 3 plus 4i over 7 plus I. So we multiply by the opposite sign there, so 7 minus I, 7 minus I. So let's work with the denominator first. All we do is we square and add. So 7 squared is 49, 1 squared is 1. And remember, I times I is I squared, which is minus 1, and we have a minus there, so that gives us a plus. And then on the top, we go through and multiply. 3 sevens are 21, 3 times minus I is minus 3i, 4i times 7 is 28i, and 4i times minus I is going to be 4 times I squared, which is minus 1, times minus 1, which is going to be plus 4. So that will give us 21 plus 4, which is 25, and 28 take away 3 is 25i over 50, and both of those just cancel down to a half. So we know now that 2z plus z star is equal to a half plus a half I. So in the form of a plus bi, so what we're going to do is replace z with a plus bi. And that's just this conjugate pair. So that's equal to a half plus a half I. So if we multiply that out, 2a plus 2bi plus a minus bi is equal to a half plus a half I. So let's bring some terms together. That gives us 3a, and 2b take away b is bi equals to half plus a half I. Okay, so I'm just going to multiply by 2 throughout, so that gives us 6a plus 2bi equals 1 plus I. So let's compare the real parts. 6a equals 1, a equals 1 over 6, and the imaginary parts, 2b equals 1, which gives that b is equal to a half. So that will give us 1/6 a plus a half bi is our value of z. Question 5. So f of z is that a and b are real constants, and so given that minus 3 plus 8i is a complex root of the equation f of z equals 0, write down another complex root. So we just take the conjugate of that, so that will be minus 3 minus 8i. So that will also be a root. So part B, hence or otherwise, find the other roots of the equation f of z equals 0. So what we have is z minus, and we're going to put in our roots, minus 3 plus 8i, z minus 3 minus 8i as the roots for our equation. So that will be sort of the quadratic that goes into that equation there. Now we should know z minus alpha, z minus beta is equal to z squared minus the sum of those two, alpha plus beta, and the product of those two, alpha beta. So in terms of trying to work out what that will give us quickly, that will give us z squared. So add those two together, the 8 i's cancel, and we get minus 6, which is plus 6z. And then the product of those, so a bit like we did earlier, 3 times 3 is 9, 8 times 8 is 64, 64 add 9 is 73. So remembering that I squared is minus 1, but we've got a negative, so they cancel. Now, you can do some long division in order to get that in that form, but sometimes you want to try and look for quicker methods to do this. Now notice that equation there can be written as z to the 4 plus 6z squared plus z cubed plus 76z squared, which becomes 73z squared plus 3z squared. I hope you can read that through the mess I've made of it, plus az plus b. So I'm going to put that in 2 parts. Now this first part is just that multiplied through by z squared, and then this part is just that multiplied by 3. It's got a 3z squared, it must be sort of multiple of 3 of this one if it goes in. So there we go, that's our factor, z squared plus 3. So what we have is f of z is equal to z squared plus 6z plus 73, which we know the roots of, multiplied by z squared plus 3. So what we need is the solution for this part here. So z squared plus 3 equals 0, z squared equals minus 3, so z is equal to plus or minus root 3 I. So there we have all 4 of our solutions, our 2 there, and the original one we're given, and our conjugate. So it says show on a single Argand diagram all 4 roots of the equation f of z equals 0. So we've got minus 3 minus 8i, so that will be there, minus 3 plus 8i, and we've got root 3i, so that's about 1.73, and minus root 3i. Okay, and then I just draw roughly lines in between. Actually, let's use a ruler and make it a bit neater. Okay, so those are our solutions to that question. Right, question 6. So 2x squared plus 4x minus 3 equals 0 is root alpha and beta. So without solving quadratic equations, we want to find a few things. So firstly, we need to know about our roots. So in ax squared plus bx plus c equals 0, alpha plus beta equals minus b over a, and alpha beta equals c over a. So if we have a look, alpha plus beta will be equal to minus 4 over 2 equals minus 2, and alpha beta will be equal to minus 3 over 2. So in part 1, they ask us to find alpha squared plus beta squared. So again, want to know, or something you can work out. So alpha plus beta squared gives that. So if we rearrange that to make alpha squared plus beta squared the subject, it's that, take away that. So it's equal to alpha plus beta squared minus 2 alpha beta. So let's plug in our values. So alpha plus beta squared minus 2 lots of alpha beta. So that will give you 4 plus 3, which equals 7. Part 2 asks for alpha cubed plus beta cubed. So similarly, alpha plus beta cubed, if you're not sure, so a bit of binomial expansion, so we're going to have 1, 3, 3, 1, then descending powers of alpha, alpha cubed, alpha squared, alpha, alpha to the power of 0, and ascending powers of beta, beta to the power of 0, beta, beta squared, beta cubed. Now this middle bit has a common factor, 3, alpha, beta, so which leaves you with an alpha there and a beta there. So rearranging that, alpha cubed plus beta cubed is equal to alpha plus beta cubed, take away 3 alpha beta, alpha plus beta. Okay, so let's plug in our values. That's minus 2 cubed minus 3 lots of minus 3 over 2 times minus 2. So what we have is those 2's cancel. We have 3 negatives there, so that's equal to minus 8, and 3 times 3 is 9, which is minus 17. Right. Part B says find a quadratic equation which has roots alpha squared plus beta and beta squared plus alpha. Now again, I'm going to go back to this form here. So if we know our roots, what we can do is we can work out sort of the sum of our roots and the product of our roots. So if we add those, that gives us alpha squared plus beta plus beta squared plus alpha, which is alpha squared plus beta squared plus alpha plus beta. And then the product of our roots, alpha squared plus beta times beta squared plus alpha. That gives us alpha squared beta squared plus alpha cubed plus beta cubed plus alpha beta. Right, so we can sort of look at these things and see what we get from there. So alpha squared plus beta squared, we worked out earlier, that was 7. And alpha plus beta, we know is minus 2. So that gives us 5. And here, alpha squared plus beta squared, that's just alpha beta squared plus alpha cubed plus beta cubed plus alpha beta. So alpha beta squared minus 3 over 2 squared plus alpha cubed plus beta cubed, which is minus 17, plus alpha beta, which is minus 3 over 2. And if you work that out on your calculator, I'll give a minus 65 over 4. So that will give us x squared plus our sum of the roots, which is going to give us, well, minus the sum of roots, which is minus 5x, plus the product of our roots, which is minus 65 over 4. So multiply through by 4, that gives us 4x squared minus 20x minus 65 equals 0. Okay, so last part, just looked at the z squared minus the sum plus the product. And that most resembles what's given in the formula booklet: cos theta minus sine theta cos theta, which is an anticlockwise rotation through theta about 0. So it's given there. So what we need to do is just compare a few things. So the minuses, we get rid of those, and so sine theta equals 12 over 13. So if we take a calculator and do the inverse of 5 over 13, that gives us 67.4. And then similarly, if we do the inverse of 12 over 13, inverse sine, and again gives us 67.4. Now that's nice because both of those give exactly the same value, so that will be our answer. So we need to state for our marks, just a bit like GCSE, our full transformation. So it's a rotation, and it's anti-clockwise, 67.4 degrees about the origin. Now, part B says a transformation V represented by the 2 by 2 matrix. Q is a reflection in the line with the equation y equals x. So this is one of those that you need to know. Reflection in the line y equals x is going to be 0, 1, 1, 0. So if you're unsure, you can go about first principles from that. And then the next part, given that the transformation V followed by the transformation U is the transformation T, which is represented by the matrix R, so find R. So it says transformation of V followed by U. So that will give us and you need to make sure that they're written in the correct order. So it says V followed by U, so V goes on that side. And then if we work that out, so those two that times those two will give us minus 12 over 13, those two times those two will give us 5 over 13. So bottom row, for the bottom left, we go through those two, so that again is 5 over 13, and for the bottom right, that will give us 12 over 13. Now, part D, so they show that there is a value k for which the transformation T maps each point onto the straight line y equals kx onto itself and state the value of k. So we're going to take that matrix there, and what we want to know is if we multiply it by our coordinates x and y, now remember y is equal to kx, so I'm going to replace that by kx. Then it maps onto itself. So what we're going to do is we're going to write two equations. So firstly, go through the top row. So we get minus 12 over 13 x plus 5 over 13 kx is equal to x. And our other one, the bottom row, 5 over 13 x plus 12 over 13 kx is equal to kx. I can go through, cancel x throughout to make things a bit easier. And if I solve either of those, so basically that's what I'm solving. So minus 12 plus 5k equals 13, 5k equals 25, k equals 5. Now I can either solve that in the same sort of way, or I can just substitute k equals 5 into there and show that I get the same answer. And so 5 over 13 plus 12 over 13 times 5 equals 5. So what we get is 5 over 13 plus 60 over 13 which equals 65 over 13 which equals 5. So there we go, we check that. So it's y equals 5x for our y equals kx. And question 7. So question 7 says prove by induction that for all positive integers n, 5 to the 2n plus 11 is divisible by 6. So we need to go through our stages. So the first one is to show it for n equals 1. So that gives 5 to the power of 2 times 1, which is 2, plus 11, which is 25 plus 11, which is 36. That's equal to 6 lots of 6. So it's true for n equals 1. So make sure you make that statement that it's true for n equals 1. So the next statement that we need to make for our next mark is to assume it's true for n equals k. So i.e. f of k is equal to 5 to the 2k plus 11. And then that is divisible by 6. There's an I there. Right, so then we look at f of k plus 1. So that will give us 5 to the power of 2 lots of k plus 1 plus 11, which is 5 to the 2k plus 2 plus 11. So rules of indices, that will give us 5 squared times 5 to the power of 2k plus 11, which equals 25 times 5 to the power of 2k plus 11. So what I'm going to look at is f of k plus 1 minus f of k. And the reason for that is I noticed that 25 lots of 5 to the 2k, take away 1 lot of 5 to the 2k, will give me 24 lots of 5 to the 2k, which is divisible by 6. That's 25 times 5 to the 2k plus 11 minus 5 to the 2k plus 11. So the 11's cancel. So that'll give us 24 times 5 to 2k. So here I just want to look at f of k plus 1. So that will be 24 times 5 to the 2k plus f of k, and 24 is 6 times 4 lots of 5 to the 2k, and so that is divisible by 6, and that we assumed was divisible by 6. So now we need our final statement for our final couple of marks. So you need to make sure you've encompassed everything that you've done above. So if f of k is divisible by 6, so f of n equals k, then it has been shown that f of n is divisible by 6 when n is equal to k plus 1. Also, it was shown that f of n is divisible by 6 when n equals 1. So hence f of n is divisible by 6 for all n. So you need to make sure you state about n equals k plus 1, and also about n equals 1.